In this sixth and final episode of the series, I finally complete the spot welder. I had expected the build to take much less time, but the delivery of the supercapacitor and the tungsten copper components went wrong no fewer than 3 times, which meant I had to wait several months longer than planned. Here you can see the front panel of the machine, fitted with almost all of the electronics, which I managed to acquire for next to nothing. It is hard to believe that the 3 digital voltmeters cost me less than €2 in total, including postage. Sensitive electronics and currents of several thousand amps do not make good neighbors inside the same enclosure. For that reason, I housed the circuit board containing the voltage comparators in a sealed steel enclosure and carefully shielded all cable connections with copper braid. Still on the to-do list are the finishing touches, the welding circuit, and that cursed high-current relay. I will tackle that problem first. To achieve the required high contact pressure between the tungsten copper electrodes, I designed a hinged relay. The solenoid's pulling force of approximately 40 kilograms is doubled by this mechanism to well over 80 kilograms. That should be sufficient to reduce the relay resistance to well below the roughly 40 milliohms measured in the previous version. Here, I am pressing one of the tungsten copper contact points into the 10 mm thick relay arm. The new relay is ready for testing. Let us see whether all that effort has paid off. 100 microohms. That is an excellent result, and roughly 4 times lower than the resistance of the previous version. I am very pleased with that. The total resistance of the welding circuit, including the internal resistance of the supercapacitor, is approximately 850 microohms when two 1 mm thick steel sheets are clamped between the electrodes. One might be tempted to assume that, at 2.6 volts, the current would be around 3000 amps, giving an initial power output of nearly 8 kilowatts. However, that is rather optimistic. A significant amount of inductance is present in the welding circuit, which limits the current during the initial phase. In addition, the resistance of the steel increases substantially as it heats up, further restricting the current flow. A current profile similar to the one shown in this graph is therefore more realistic. Fortunately, there is still a considerable amount of power available. Thanks to the very low resistance of the welding circuit, it is substantially more powerful than the earlier videos featuring that hastily thrown together bodge job. And now that the final obstacles appear to have been overcome, it is time to close up the enclosure and start making some test welds. Let us begin where most YouTube videos end, welding together two thin strips of metal. For two strips each 1/4 of a millimeter thick, a great deal of energy is not required. I will start with a capacitor voltage of 2 volts and stop the weld when it falls to 1.5 volts. In theory, that corresponds to just over 2000 joules of stored energy, although roughly half of that is consumed by the welding circuit itself. The weld looks excellent. There is very little discoloration, and the weld proves to be stronger than the surrounding metal, tearing a hole in it when pulled apart. Now for a slightly more demanding task, welding together two steel strips, each 1 mm thick. I will increase the starting voltage and put approximately 2000 joules of energy into the weld. And now we are going to make things a little more challenging. This time, I am welding 0.5 mm stainless steel to a 2 mm steel plate. This also appears to have produced an excellent weld. I will test it in a moment. Here, in slow motion, is what happens when you weld together two steel strips, each 0.7 mm thick, while the pressure applied by the electrodes is too low and the welding energy is too high. The molten steel is blown out from between the electrodes. It is a spectacular sight, but it is not what is supposed to happen. This demonstrates that welding different types of steel together, in this case 2 mm mild steel and 0.5 mm stainless steel, is often perfectly feasible. Here too, the weld test shows a hole in the thinner material, showing that the weld itself is stronger than the sheet being tested. This machine produces strong, high-quality spot welds, and controlling the amount of energy delivered is remarkably straightforward. The shower of sparks we saw a moment ago also produced a strong weld. However, because this is a hardenable steel, the rapidly cooled weld becomes extremely brittle. That is generally not something you would want and is best avoided. But this machine does, of course, have its limits. Although it more or less manages to weld together two steel plates with a combined thickness of 4 mm, the available energy is clearly insufficient. The weld has not formed a proper nugget and is not strong enough. This would probably be resolved if I installed the second supercapacitor, for which I have already left space in the enclosure. For the time being, however, there is no need for it. And with that, we have come to the end of this video and of this series. I hope you have enjoyed it and perhaps learned something along the way. I look forward to seeing you again in the next video. At the moment, I have no idea what the topic will be, so your suggestions are very welcome. Feel free to let your imagination run wild in the comments.